today I'm going to share some work we did running quantum approximate optimization on the Sycamore processor. So problems in discrete optimization are prolific throughout industry, logistics, finance, machine learning. The possibility of quantum enhanced optimization has really driven interest in the field. In general, these problems can be stated really broadly as the goal of finding an object X from a finite set of objects that minimizes some cost function C of X. Despite this historical interest in quantum optimization, there's always been this lurking historical problem. And to see what that is, first we have to say that the very basic prerequisite for quantum optimization is that you have to make the quantum system feel the problem you're trying to solve. The quantum computer needs to compute the cost function. But how we do it in practice is we query the cost function to phase basis states. The historical problem is that the physical limitations of the device can constrain you to particular families of cost functions, which are easy to solve classically. Annealers certainly have this problem, but recent gate model experiments on quantum optimization have also fallen into the trap of sticking to hardware native cost functions. And what do I mean by a hardware native cost function? Well, we're going to focus on discrete optimization problems of a particular form given by the formula you see on the screen. These are quadratic binary cost functions. All discrete optimization problems can be mapped to this with some overhead. But the two local structure means we can visualize the cost function as a graph. If the cost function's graph matches the hardware's topology, it's very simple to query the cost function on a quantum device. However, it should come as no surprise that these problems are typically not industrially relevant and easy to solve heuristically. So in this study, we studied random instances, both of these tailored hardware grid problems, but also prototypical computer science problem families that don't match the device, namely 3 regular max cut and a fully connected Sherrington-Kirkpatrick model, SK model. And for non-native problem graphs, we have to perform swaps to move qubits around to perform all the desired interactions. And we'll see the impact of this overhead later. So for example, to implement a 17-bit all-to-all connected phasing unitary for the SK model, we repeatedly apply this composite operation given by the purple box, which is composed of the 2 body cost function terms and a swap so that we could bubble the logical qubits past each other. And you could sort of puzzle this out on your own, but if you do n rounds of this interaction, each pair interacts once, allowing you to implement the full cost function. Luckily, there are utilities in Circ to help you with these sorts of tricks in compilation. For this work, we use the specific prescription of the quantum approximate optimization algorithm, or QAOA. And this prescribes repeated alternating applications of a problem unitary and a driver unitary, UC and UB, where the driver unitary is relatively simple. It's single qubit parameterized X rotations that drive transitions between the basis states. This is a variational algorithm where each layer has 2 parameters, also called angles, gamma and beta. We sample from the quantum device for a particular parameter setting. We sample bit strings, compute how well they solve the problem, and then use a classical optimizer to suggest new parameters, which improves the quality of solutions. So the number of layers is given by this hyperparameter P. So there are 2 P parameters to optimize. For P equals 1, there are only 2 parameters, which lets us make a nice diagnostic landscape plot and demonstrate the ability of a classical optimizer to find the maximum. So now we'll get into showing some data. This is for what we've termed hardware grid problems at 23 bits. The graph is shown on the left. In the middle, there's a noiseless simulation of what we expect the landscape to look like. where the color gives the average quality of solutions normalized, and higher is better. And on the right, we show the experimental results. In here for the hardware grid problem, we could see clear agreement between the noiseless simulation and the experimental results. Additionally, we initialized a classical optimizer from the red square in the experimental plot, and it was able to quickly find the maximum in parameter space, whose theoretical position is shown with a blue star in the noiseless simulation plot. And these sort of world-class results are possible due to good hardware, particularly very limited crosstalk on the device. There's a nice developing tradition of using these plots as a visual representation of what's going on. I personally really like that. And the previous state of the art for these plots was shown at n equals 20. And this is n equals 23. We can also show a landscape for the much more complicated SK model, here at a more modest size of n equals 11 bits. Again, the noiseless simulation is in the middle and the experiment is on the right. The hills and valleys aren't as sharp as before, but they're clearly there and in the correct location. The classical optimizer is still able to climb uphill. And this is, again, sort of best-in-class performance for what you'll see is a very deep circuit. In the previous complete graph demonstration, maxes out at n equals 4. So this is sort of considerably larger than anything shown before. And to investigate this a little more fully, we'll move to a regime where we compute the optimal parameters classically. So we can just use those. We can compare the performance of many random instances at a variety of problem sizes and circuit depths. So this plot has the number of qubits, aka problem size, on the x-axis, the quality of solutions on the y-axis, higher is better, where the upper band of square points corresponds to noiseless simulation, and the lower band of circle points is actual data from the device. And at each problem size, we tossed random instances of this graph. These blue points are hardware grid problems. And we see an interesting feature. After about a problem size of 10 or larger, the performance seems to level out. This can be expected from a simpler compilation in the low degree of the problem graph, but only assuming a local error model, which requires good hardware. And this sort of plateauing behavior suggests that we can likely scale these implementations up to arbitrarily large sizes and still get signal from the device. There's a slightly different story when we do the same thing for the Sherrington-Kirkpatrick model. This is at p equals 3, and the square noiseless simulation points in the top band sort of track with what you'd expect for hardware grid problems, but the actual implementation on the device has qualitatively different behavior. So this is p equals 3, and at modest problem sizes, sort of 10 and fewer, it still does a relatively good job with performance, with definite signal in the performance of the device. But clearly performance degrades with problem size, and scaling up could prove to be a challenge. And if you take a brief look at the statistics reported on the side, you can see that the compilation overhead makes the SK circuits much more difficult for the same problem size, and going up to 153 layers of 2-qubit gates shown on this plot. Finally, we can look at how things change versus depth. There's this hyperparameter P that controls the depth of the circuit ansatz. Without noise, higher P is always better. That's this green line. Noise makes it a trade-off. That's the blue experimental data. Experimentally, for the hardware grid problems, we see a relatively flat curve, but peaks at p equals 3. And in fact, we can, instead of averaging over many instances, we can look on a per instance basis and see that over 50% of the problems studied are maximized performance at p equals 3. And this is really exciting because it's going to be important to have to scale this hyperparameter P to get good quality solutions on problems of interest, and the previous best reported that the performance at p equals 2 could match that at p equals 1, where here we show clear improvement at higher p. In summary, diagnostic landscapes show the device working well. We can perform variational optimization. Hardware native problems show desirable features like n-independent noise and higher performance for deeper circuits. Real problems require more compilation, which can lead to challenges scaling up. We think QAOA has been effective as an unofficial benchmark of hardware performance on problems of interest. And we'd love to see more non-native graphs being solved and data being reported. Thanks so much for everyone tuning into the live stream. And now I'll pass it back to Marissa.